Yes. So we'll just directly go into the factors which affect the ESR G value of particularly the inorganic complexes. There are a number of factors, and we are going to cover in our discussion a couple of important factors. First of all, the spin state of the complex. You know, the inorganic complexes can be classified into low spin and high spin. And it is the electron of the d orbital, unpaired electron of the d orbital, which is giving us the ESR spectrum. Is it not? Fine. Now, there is an observation that if the electron couples more with filled orbitals, then it will have a positive contribution to delta G. So the G value increases. If the coupling is with empty orbitals, the G value decreases. After all, what is that G? The G is actually the delta G, because in ESR, we know that the standard reference, internal standard, is the G of the electron itself. Of course, we can also use internal standards, free radicals, whose G value is close to free electron also. But theoretically, at least, that's the reference. So what is the delta G value? Depends on G value. G is fixed. So any positive contribution to the delta G should increase the G value. Negative contribution to delta G should decrease the G value. And when we are looking into spin states, it's the orbitals which are filled or empty tell whether G is more or less. For example, take Fe3 plus complex, high spin complexes. It has G in between 4 to 4.5. Very high G, right? What is the G of free electron? 2.0023. Even the free radicals, the G is same almost. So look at this high spin complex Fe3 plus. By the way, Fe3 plus, how many d electrons are there in Fe3 plus? How many d electrons?
5, sir.
Very good. 5. Yes,
5.
correct. 5. And all 5, if the d orbitals are degenerate, all 5 are unpaired. So Fe3 plus represent a system with maximum magnetic moment, right? With 5 unpaired electrons. So that should be very active in ESR with 5 unpaired electrons. But you know, that is when the d orbitals are degenerate. But when the crystal field is applied, what happens to the degeneracy? It breaks. Anyways, but for high and low spin, you can also predict your valence bond theory, right? High and low spin complexes. So in the high spin complex, how many unpaired electrons? And in the low spin complex, how many unpaired electrons? Okay, in the high spin complex, there are 5 unpaired electrons. All 5 are unpaired in the high spin complex. Whereas in the low spin complex, only 1 is unpaired. So if you look at the orbitals of the high spin, when you write the valence bond energy levels and analyze, there are no empty orbitals for the high spin complex, which has 5 unpaired electrons. Whereas for the low spin complex, there are 2 empty orbitals. 2 empty orbitals. And if there are empty orbitals in the metal ion, the G will decrease. If there are more filled orbitals, the G will increase. Therefore, the Fe3 plus high spin complex gives you G of 4 to 4.5. What is the G value? Observed G value of Fe3 plus low spin complex, almost close to 2. We are comparing in between low spin and high spin. So the spin state is, of course, a big factor which influences G. Now, what is the application of ESR now? Because we have discussed this point. By looking at the G value, you can predict the magnetic behavior of the complexes. Is it not? A G value very high indicates high magnetic moment, therefore high spin complexes. So in any spectroscopy, we will go in reverse direction. We get the experimental G value or the spectrum and backtrack the structure. Similarly, a high G value always indicates high magnetic moment of the complexes. Fine. Now, like the spin state, even the oxidation states of the metals in the complex ions also play a role. For electron poor complexes, so electron poor means they have lost electrons. Therefore, the oxidation state is more. Oxidation number is more. So electron poor means higher oxidation states. The G is less than 2. Whereas for electron rich complexes, lower oxidation states, J is more than 2. Fine. So when you are within the metal ion, same metal ion, G value is also helpful to indicate the oxidation states of the metals, at least comparatively speaking. So these are the two factors, the spin states and the oxidation states, which influence the G value. And of course, I don't mind repeating this again. Why is G value so important for us in our discussion? Because it is the chemical shift equivalent of NMR. Because of G, it is a G value which characterizes your spectra, basically. Otherwise, if there is no role played by the G, all spectra would have looked alike, would have of almost no use to us. Because the G value changes, the position of the peaks also change. You remember your fundamental equation, right? So your delta E or H mu, the frequency is dependent on G value, directly dependent on G value. Therefore, G value is the one which gives the characteristic signals from the compounds, complexes. Fine. Now, we'll move on to one more factor. That is, as I told you in my previous class, for a complex, the contribution from the orbital angular momentum is significant. Unlike in free electrons or free radicals, where there is no contribution from the orbital angular momentum. So your Landis G factor, the L term becomes 0. So when the L term becomes 0, only the S and J remains, and J becomes L. Therefore, G becomes 2 almost. But here it's not like that in our inorganic complexes. The orbital angular momentum contribution is significant. Therefore, we have to look into. That is why we discussed spectroscopic term symbols in our previous class. Now, spectroscopic term symbols also tell you the extent of coupling of spin angular momentum and orbital angular momentum, because the term symbols inherently have a term L plus S, that is J. So what is J? It is a quantum number obtained after coupling the quantum number of orbital and spin angular momentum. Therefore, working with spectroscopic term symbols is important when we are discussing orbital angular momenta and spin angular momenta coupling. Now, therefore, when there is more contribution from the orbital angular momentum, the G value changes. Changes means it deviates from the free electron G value. When there is no contribution at all, it remains at free electrons G value. And of course, there is also the orientation of this orbital contribution, which is important, which we are going to discuss later. But now at least we will see one example where the orbital angular momentum contribution is having a say on G value. You look at this. Okay, anyways, before that, now in a DN complex, that means N represents any number of electrons, D1 to D10 or D1 to D9, is which is okay. Now, like we worked out one example for a D1 system, spectroscopic term symbol, in our previous class. Like that, you can work out spectroscopic term symbols for any given DN system. But you see that, like I gave you an example, if D2 system example, D2 system, let us take. So your L value for D is equal to what? L value is 2. Small L value is 2. So when there are 2 electrons now coupling, so your capital L value becomes how much? Capital L value becomes 2 plus 2, 4. 4, 3, 2, 1, 0. So these are all the
Both 0, 1.
yes. So these are all the possible L values. Now, when you write so many L values, of course, and corresponding term symbols, you can wonder of all these possible states. These are called spin states. Yeah, basically these are all spin states. Your spectroscopic term symbol represents a spin state. Okay, so one now, which is the ground spin state? Is it not? For that, Hund's rule also. Hund's rule tells some guidelines for this also. I hope you remember the Hund's rules of maximum multiplicity and all in quantum mechanics. So the same Hund's rule also gives some indications on which is the ground state. Now, which is the ground state depends on two conditions: whether the system is half full, half less than half filled, or more than half filled. So, a systems from D1 to D4, the ground state is the one where J is minimum. Okay, so J is minimum means, so when you are coupling J, you are going to couple L and S, right? L plus S, and you go on doing the same thing like you did for two L's, L small l plus small l. So you do J is equal to, for example, L is 3 and S is equal to 1. So 3 plus 1, 4, 3, 2, 1, till how much? Till J L minus S. So if L is 3 and S is 2, 2. So you get J is equal to 2, one state. That will be the ground state. So the ground state is the one which has minimum L minus S, with minimum J value. So of all the possible J values, which will be the minimum? The one obtained with L minus S operation, right? So that's the minimum J value. And if it is more than half filled, so D6 to D9 systems, you have J maximum will be your ground state. Okay, so what is Hund's rule telling you? Which is the ground state? For D1 to D4, minimum J is your ground state. For maximum, I mean for D6 to D9, maximum J is your ground state. Okay, fine. Now, why this minimum J and maximum J has become focus of our discussion? Because minimum J means minimum coupling of orbital angular momenta. Okay, maximum J means maximum coupling of orbital angular momenta. Now, let us see one example. Mn2 plus is a D5 system, and for D5 system, L is equal to 0. Okay, so when L is equal to 0, L is, of course, the orbital angular momentum quantum number. So when L is equal to 0, there is actually no coupling at all with the electron. So what would be its G value when L is equal to 0? What is its G value when L is equal to 0? I'm telling there is no orbital angular momentum contribution when L is equal to 0. So what should be its G value? Oh my God. I mean, we have been discussing this point since last 3 classes again and again. What is the G value of a free electron? Yeah? 2.0022. When will, yes, when will there be, why, for example, inorganic complexes, the ESR G values deviate from this value too much? What is the reason? What is the reason?
Due to coupling.
Due to coupling with orbital angular momenta. Yes, is it not? Orbital angular momenta. Now, if L is equal to 0, that effectively means there is no orbital angular momenta. So what should be the G value?
2.00.
Yes, correct. Good. That should be close to the value of the free electron. So now these are all things we are theoretically telling. Is it experimentally so? Yes, because in Mn2 plus 12, the same thing happens. G value is equal to 2.00. So this proves our point that orbital angular momentum contribution has a big role to play in the G value. Now, Let us take a system with having orbital angular momentum contribution. So D should not be 5. It should be either more than 5 or less than 5. So D1 complex, vanadium 4 plus, and since in vanadium 4 plus, it's the D1 means less than half filled. So ground state is the one with minimum J. So with minimum J means minimum coupling of orbital angular momentum. Therefore, G value is reduced. Okay. So if the extent of coupling with orbital angular momentum is less, G value is also less. Now we will take one system more than D5, one copper 2 plus D9. So for a D9 system, which is the ground state term symbol, which is the ground state term symbol, is the one with maximum J. So L plus S. So there is more coupling with the angular momentum. Therefore, the G value increases. Fine. So this is why we have to look into the contribution from angular momentum from. That's why I solved that. That's why I made you to work out the spectroscopic term symbols a bit, because ground states are important. Anyways, so till now, how many factors we have covered? The spin states, the oxidation states, as well as the uh, contribution from the orbital angular momentum. With examples we have seen. Now we will move on to something a bit interesting. Now, uh, theoretically, if an electron is absorbing and giving us an ESR spectrum, how many uh, of course, now let us think there is no hyperfine splitting. So how many, if there is no hyperfine splitting, how many lines do we expect? If there is no hyperfine splitting, there is no zero field splitting, nothing. How many lines do we expect? Single line, right? So single line means only one G value, because it's a G value which is important to us from the spectra. Now, to our surprise, if we see some spectra of some complexes, we will get two G values. You see, a G at 2.101 as well as G at 2.434. Two G values from the same complex. And why is this? Is the question. Fine. And please note how to correlate the G value and the field. At low field, we will have higher G values. It is similar to your NMR. Chemical shift increases towards the left of the spectra, right? Where the field strength decreases, it's down field. So higher chemical shifts towards the down field. Similarly here, higher G is towards down field. So how do you calculate G value here? Simply you take the field strength at this point, and you know the operating frequency of the spectrometer, whether it is X band, all those things. You know the microwave frequency at which the spectrometer is operating. Use these two terms in your fundamental equation and get the value of G. Okay, so now you are observing two peaks. You have done all your calculations and you are surprised you are seeing two G values. Now, why does this happen? Is our question. This is because a phenomena called anisotropy in G values. As we know, the anisotropy simply means there is some inequality, there is some heterogeneity somewhere. That is why the anisotropy is happening. Now, where is that inequality or heterogeneity happening? That is what we have to go into account for in our next discussion, next part of the discussion. You see, anyways, I've just given you a formula down. That's what I told, how to calculate G. You use your B and then values. And once when you look at the alignment of the spin states with respect to the applied magnetic field. Fine. Now we have two extremes of orientations of the spin states. One is parallel with the external magnetic field, and one is perpendicular. Now, let us simply for our argument's sake, let us designate this G as parallel and this G as perpendicular. Okay. In fact, if there is a spherical symmetry in this complex, you cannot distinguish G parallel and G perpendicular. G parallel and G perpendicular become distinguishable only there is distortion in the symmetry. Fine. So what are we now slowly capturing? The geometry of the complex has an effect on G values, or we can tell that the symmetry of the complex has an effect on G value. How? That is what we are accounting. What is the theoretical basis of this? You can draw an axis anywhere inside this sphere. Basically, it is called an ellipsoid. If the axes are distinguishable, then this becomes anisotropy. If the axes are indistinguishable, then this becomes isotropy. Now, when the axes become indistinguishable, under two cases. First case is when the molecule is in rapid motion. So it is freely tumbling in space. In such case, what happens? But your applied field is not freely tumbling in space. It has a direction, fixed direction. One direction is fixed for your applied field. What is the direction of the field of, for example, the local magnetic field created by your free electron, I mean, created by the unpaired electron, depends again on the position of this molecule. But since in the free space, I mean, when the molecule is in rapid motion, example in the gaseous state, let us assume, it has any orientation possible. So in such case, what happens? Because of random motion, all orientations become equally probable. In such case, again isotropy comes into picture. Okay, so now let us freeze the sample. Like instead of taking the ESR of the gaseous sample, where the G is isotropic. Always for gaseous samples, the G is isotropic. Let us freeze the sample. Let us make it crystalline in solid state or very dense viscous liquid state. In such case, what happens? The molecular motions become minimum. So when the molecular motions become minimum, the magnetic moment's direction of the local magnetic field created by the electron becomes directional. It was not directional before when the molecule was freely tumbling. Now it has become directional. So the anisotropy comes into picture. So does it mean that all solid samples which you use for recording ESR should give you different G values? No. There is again some, okay, see, I have 10 more minutes. No problem. Once the class is over, I will reschedule this. You please relog in because I require another 10-20 minutes or so to complete this discussion. We have to complete this discussion this week. Next week onwards, we move on to new topic. Oh, fine. So now, does it mean that all solid samples will give you different G values? No. Then why few solid samples give single G value and few do not? That is because okay, now let us think we are focusing only on inorganic complexes. Some inorganic complexes give single G value, some inorganic complexes do not give. That is because of the symmetry in the crystal field. If the crystal field is symmetric, there is a single G value. Okay. If the crystal field is asymmetric, or if the crystal field symmetry is distorted, then you get multiple G values. Fine. So you remember at least this much. If the crystal field is symmetric, you get single G value. If it is not, you get different G values. Now, the picture of the orbitals, shape of the orbitals is required for our discussion. That's why I've just shown you the slide. You know, in a crystal field, example octahedral field here, we can partition our G value, overall G value, into three components: Gx, Gy, Gz. Okay, let us assume like that. Make an argument like that. And these Gx, Gy, Gz are all our principal axes. Now, we just have to simply tell, are Gx, Gy, Gz distinguishable or indistinguishable? That's all. If Gx, Gy, Gz, these are all G's on mutually perpendicular Cartesian coordinates. If these three are distinguishable, then you get different G values. If they are indistinguishable, you get single G values. Now, what did I tell? The G value is determined by the extent of coupling with so many things. Example, orbital angular momentum. It also depends on the electron density around this. And who gives this electron density? The ligands. Fine. So if the electron density around this unpaired electron on the metal ion is spherical, is symmetric, you get single G value. Now, in what type of symmetries you get a spherical field? In what type of, in what shape of the complexes you get? Shape is not a very good word. In what type of symmetry in the complexes you get spherical fields? Okay, let me tell. There are different symmetries of the inorganic complexes, right? Complex ions. At least you remember two basic type of symmetries, the octahedral and the tetrahedral. Fine. So let me ask, in an octahedral symmetry, I'm not talking about geometry, in an octahedral symmetry. So what do you mean by, what is the difference between octahedral symmetry and octahedral geometry? In octahedral symmetry, all 6 ligands are equal. So metal is bound to L ligands, 6 ligands, and all L are equal. Example, it can be something like copper H2O6 or iron CN6, like that. So that's what symmetric field, octahedral fields. Why it is symmetrical field? Because you have 2 ligands along every axis. You have 2 ligands along x-axis, you have 2 ligands along y-axis, you have 2 ligands along z-axis. So the G, which we have partitioned amongst 3 axes, so the chemical environment is same, because the field is, crystal field is spherical. You get a single G value for octahedral symmetry complexes. Okay, but this octahedral symmetry, of course, also the tetrahedral symmetry, that is also spherical symmetry, you get single G values. And if you get a single G value, then we call that is isotropic spectrum, isotropic G values. But in all cases, spherical field is not obtained. You can distort that field. Instead of it making fully symmetric, you can make it axially symmetric. Okay, so what do you mean by this axial symmetry? Now, of these 6 equal ligands, you replace 2 ligands with some other ligands. Okay, so let it be like our metal ion is metal complex is not MA6 type, or A is a ligand, rather MA4A2 type. Okay, MA4A2 type, and these, I'm sorry, I'm extreme sorry, MA4B2 type, B2 type. There are 4 A ligands and 2 B ligands, and these 2 B ligands are occupying the axial positions of the octahedral geometry. Now you look at the difference. Now I call it octahedral geometry, not octahedral symmetry. Octahedral geometry means simply the octahedral shape. Octahedral shape. Octahedral symmetry means you're applying the symmetry operations and giving it a point group octahedral OH. That is what octahedral symmetry means. Okay, So now the axially symmetric complex you have prepared. Now you record the ESR of that, you will get two G values. Why? Because no longer your Gx, Gy, Gz are equivalent. You have G, you have the electrons magnetic moment interacting differentially with respect to different orientations. Therefore, in such cases, in axially symmetric species, the G values differ. You get two Gs in your spectrum. So basically, for example, the spectra which I have shown here should be from axially symmetric complex because you have two G values in that. If you have a single G value in your complex, what do you tell? It is an octahedral or a tetrahedral complex. You have two values, it is axially symmetric. Fine. So in that case, your axially symmetric G parallel and G perpendicular are different. In fact, G parallel is the one which gives you okay, see here, G parallel with higher G values, G perpendicular with lower G value. Yes. So principal axis Gx, Gy, Gz, they become inequivalent. What is the relationship now in axially symmetric species? It is X and Y are equivalent and both are unequal to Z, Gz. What are the examples of such complexes? Trigonal bipyramidal, square pyramidal, square planar, and elongated octahedral geometries. So I was talking about elongated octahedral with the example of MA4B2 complex. Now instead of replacing two ligands differentially on the axis, you simply remove them. So if you remove two axial ligands from an octahedral geometry, it becomes square planar geometry. So square planar is an example of anisotropic G values. Whereas square pyramid even is again anisotropic G value. Trigonal bipyramidal, the best example for anisotropic G values. So what is the take home point here? What is the summary of the story? That the geometry of the complex plays an important role in deciding the G values. Fine. Okay. So you please look at this. I'll just okay. Fine. I just stop here and reschedule immediately.